Now let us take a very simple continuous bag of words based model with only one word in the context to explain the CBOW based architecture. Actually, CBOW based architecture contains three identifiable layers: input layer, hidden layer and output layer. The number of nodes in the input layer and output layer depends upon the vocabulary size we use, and the number of nodes in the hidden layer represents the dimensionality, and it may vary from one word to maximum vocabulary size. In the current context, suppose we have a three word sequence like latent, Dirichlet, allocation, and we know these two words, but allocation is missing. So in this case, the task of the system is to identify the missing word which is missing from the context and next to the context. Now in the current architecture, we have input node W1, W2, W3, W4 and W5 at input layer with input variable x1, x2, x3, x4 and x5. We fed value x1 is equal to 1 and x2 is equal to 1 as both input variables are associated with our context word latent and Dirichlet. For the rest of the words or input parameters, we put the value as a 0. Now the next layer is the hidden layer. Here we use three nodes h1, h2 and h3. However, we can take minimum node 1 like h1 and maximum node like 5 nodes from h1 to h5. Here W11 represents the weight of neuron from input layer node W1 to hidden layer node h1. Similarly, W12 represents the weight of neuron from input layer node W1 to hidden layer node h2. This matrix represents all such weighted representations. Similarly, the next layer is the output layer. Here we used 5 nodes in the output layer, O1, O2, O3, O4 and O5, and here W-11 represents the weight of neuron from hidden layer node H1 to output layer node O1, and W-12 is the weight of neuron from H1 to output layer node O2. This matrix represents all the weighted representation. In the continuous bag of word based model, we first train the system. To train the system, we first take the training example and apply forward pass. After that, we check the error. In case error detected, then we apply backward pass or back propagation, and the main purpose of all back propagations is to correct the weight of neuron or optimize the weight of neuron. We repeat this entire process until we get the optimal weight of all the neurons, or we can say that optimal weight of all the neurons in these matrices. After getting the optimal weight of all the neurons, we can use this trained CBOW model to predict the next word for the given sequence. As we discussed here, after that when we will pass the latent and Dirichlet as input, then it will automatically give the high probability score allocation as a next word for our context which contains latent and Dirichlet. So now let us start in a step-by-step fashion how we can train the CBOW based model. So the first phase of the system is forward propagation and weight calculation. In the forward propagation, we will calculate the weight at hidden layer node H1, H2 and H3. Here, different from traditional artificial neural network, we will not use any sigmoid calculation. Actually, in artificial neural network, For each node we use two different calculations. The first is summation, and second part of is the calculation of activation function. The activation function generally is a sigmoid of sum of all values, or 10h of sum of all values. But different from traditional artificial neural network, here we will not go through this phase. We will just take this summation phase. So the value at node h1 will be like sum of weight of this neuron into the input parameter, plus we will just check all the connected neurons which are connected to hidden layer node h1, their weight multiplied by their input parameter. So it may be, the second may be like w21 into x2 and so on. Similarly we can calculate the weight of h1. Similarly we can calculate the weight h2 also. The weight of h2 will be like w12 into x1, and similarly w22 into x2, w32 into x3, w42 into x4, and w52 into x5, like this. Similarly we can calculate the weight of node h3. Here we can represent it in a more generalized fashion like this. Here Wt is the transpose of matrix that we used here. Here x represents the input parameter values. After calculation of the weight of nodes of the hidden layer, the next part of the forward propagation is to calculate the weight from hidden layer to output layer. Here, to calculate the weight of each node, we apply two different calculations. The first calculation is association function, or we can represent it through a summation sign, and next part is the calculation of softmax function. So now let us start with association part. The association part is just sum of weight of all neurons which connects to the output layer node O1 and the associated hidden layer node's weight. So we represent the association score for node O1 as net O1, and net O1 we can represent it as a U1 variable, and it is the weight of neuron through H1 to O1 into score of hidden layer node H1 plus weight of neuron from H2 to O1 into score of hidden layer node H2, weight of neuron from H3 to O1, which is W-31, and weight of hidden layer node H3. Similarly, we can calculate the association score or net score for O2, O3, O4 and O5. In a more generalized form, we can represent the entire calculations through a product of matrices. Here W-T is the transpose of matrix which represents weight of all these neurons. This is the now the next part is to calculate the softmax output. So forward propagation, calculating the softmax output. Actually the softmax output for any node O1, we can represent it through variable y1 also, is can be given as e to the power net O1. The net O1 score that we calculated here is the net sum of all weights which coming to this, and this will be our out O1. So out O1 will be e to the power net O1 and divided by the sum of net score of all other nodes to the output layer. We can represent it in a short form, as we say that we represented net O1 through U1 here and net O2 as U2 here. So the entire representation can be written like this also. Similarly, we can calculate the out O2 function also. It seems like a probabilistic score, and similarly we can calculate the value of out O3, out O4 and out O5. So we can generalize this the softmax output of any word wj with respect to the given input context word wi can be given by the conditional probability in terms of exponentials like this, and represented as variable yj. This is e to the power net oj divided by summation. This is another representation of this part, and we can now again rewrite it in this form, using a short variable representation. Now after the calculation of forward score, we have a prediction score out O1, out O2, out O3, out O4, out O5. Now the next phase is to calculate the error. We use this calculated error and backpropagation to correct the weight of all the neurons between hidden layer and output layer and input layer and hidden layer. So now let us start the error calculation. Here we have some assumption, let W0 is the actual output word and Wi is the given input context word. In this case, our actual output word W0 is allocation and our input context is latent and Dirichlet, and V is the size of the input context. So here our training objective is to maximize the conditional probability of observing the actual output word W0 given the input context word Wi. Thus the loss function can be defined as by maximizing probability of W0 given the input context Wi. This is equal to maximizing Wj star, where J star represents the index of the actual output word, and which may be equivalent to maximizing the log of Yj star. Here you can revise what is Y. Y represents the softmax output. So here maximizing the softmax output of the word having index J star. So for that we can take the log also. For example, in our case the word W4 shows the actual output allocation for the context latent and Dirichlet. So in this case we can calculate the error EO4, which is equivalent to log probability of W4 with respect to the given context Wi which is equivalent to y4 log y4. So as per the calculation scheme used here and here, our O4 or y4 will be equal to u4 divided by entire summation. So here we will use the same thing, and this is equal to this, and after solving we can get this expression. Now as we want to minimize the error, so we can take E as a negative of log of probability of conditional probability of word w0 given wi. So in the current case, our error will be equivalent to log E of EU1 plus EU2. E is represented as exponential here, exponential of U1 plus exponential of U2, and like that. And now we can generalize it like this, means instead of using this form we can convert it in the summation form by using sigma, and we can replace our U4, which represents the actual output word, net score of actual output word. So we can represent it like U4. You can again rephrase the concept. Here our U1 is the net score of word O1. Similarly, U4 will be the net score, this part association or net score of output node O4. So this is the net score of the actual output word. This loss function can also be understood as a special case of cross entropy measurement between two probabilistic distribution. Also, now we can take the derivative of E with respect to U4. So our derivation, this is a simple derivation. So this is our generalized error function that we will use in entire calculation. Now we can take the derivative of E with respect to U4. The process of derivation is just a simple derivation. So when we will take the derivation of this part, so this part will be very simple, because derivation of log x is equal to 1 by x, and similarly we use another derivation concept like is equal to e to the power x. So we'll use these two property of derivations in the derivation. So this will be our score, and this is the next score, which is equal to 1. Now this is the case when we are using the net score of output 4, which actually represents the word we are looking for. So in this case, this part and this, so in this case the derivation of this part here is 1. Now we can generalize this equation 7. Now suppose we take derivation of E with respect to some node uj, then our derivation will be like this. This is again the same thing like we use here, this part, and this part will go here, and this is the next derivation. We can represent this part as Tj, and the entire error is equivalent to Ej. Now we have two cases. The first case is Tj is equal to 1. So when Tj will be equal to 1, when our node j will represent the actual output word, and it means Tj equal to Tj star. Otherwise Tj will be equal to 0. Now let us start the backpropagation between output layer to from output layer to hidden layer. The main aim of this backpropagation is to update the weight of all neurons from hidden layer to output layer, that is W11 dash, W dash 11, W dash 12, W dash 13, W dash 14 and W dash 35. Means we have to update this matrix. So as we use in the traditional backpropagation, we will take the gradient of E with respect to W dash 11. So let us start with W dash 11. So this gradient will be equivalent to, so here in this case we will apply a chain rule. Now we can extend this gradient as derivation of E01 with respect to U1, and taking derivation of U1 with respect to W dash 11. Now as we already calculated this part here, so this is our calculation scheme. dE, taking derivation of E with respect to any node uj generally gives this score. This is the output score yj. You can refresh here. Yj is equal to out function, so y1 is equal to output softmax output function of node O1. So here it will be equivalent to E1 softmax output of node 1 minus 0. As this is not the actual output node, we can represent it as E1. Similarly we can calculate this part. So here we will take U1. Here our U1 value is, here we will copy this part and put here, and take the derivation with respect to W dash 11. It gives the output score H1. So our gradient of E01 with respect to W dash 11 gives the score E1 into H1. Now we will use this gradient and update the weight of neuron W dash 11. So the new weight of W dash 11 is equivalent to old weight of W dash 11 minus new. New is the known as learning rate. We can put any value from 0 to 1 in the range of 0 to 1 as a learning rate, and DE01 a derivation of and a gradient of E01 with respect to W dash 11, which is here, and this is the final value of a new value of W dash 11. Similarly we can update the weight of all other neurons like W dash 12, W dash 13 and so on. Now the next phase of the backpropagation will start, which will go from hidden layer to input layer. In this phase, in this backpropagation phase, we will update the weight of all neurons from hidden layer to output layer, that is W11 and W12 and so on. Means our target is to update the weight of entire matrix this entire this matrix. So as usual, the first part is taking gradient. So we will take the gradient of E with respect to W11. Now we can extend this gradient score as dE, derivation of E with respect to H1 into derivation of H1 with respect to W11. Now taking the gradient of E with respect to W11, this is equivalent to taking derivation of E with respect to H1 into taking derivation of H1 with respect to W11, as here in this case the backpropagation error will come from 5 different paths, from O1, from O2, from O3 and from O4 and then from O5. So this part can be extended into this form, means error which propagates through node O1, which will be equivalent to derivation of E with respect to U1 into derivation of U1 with respect to H1. The next error which propagate from O2 to H1 is derivation of E with respect to U2. U2 is the net input function at O2 into derivation of U2 with respect to derivation of H1. Next is when the propagation error which comes from O3 can be calculated by this part, derivation of E with respect to du3, which is the net association function at O3. We can recheck that what is our net association function. So you can check that net O3 is U3, and that we have calculated here. So again, now the next error which propagates through the output layer node O4 can be calculated by this expression, which is dE, derivation of E with respect to U4 into derivation of U4 with respect to H1, and U4 is the net association function at O4 plus the error which propagates through output node O5, which is equal to derivation of E with respect to U5, which is net input function at net input at O5 into derivation of U5 with respect to H1. After calculation of all these derivations, actually the calculation of all these derivations is too easy, because this part is already calculated. Derivation of E with respect to U1 is already calculated here, which is E1. Similarly, the derivation of E with respect to U2 will be E2, derivation of E with respect to U3 will be E3, derivation of E with respect to U4 will be E4, derivation of E with respect to U5 will be E5. Now the next part is to calculate the derivation of U1 with respect to H1. Now to calculate the derivation of U1 with respect to H1, this is very simple. So we have U1. When we calculate the derivation of U1 with respect to H1, then all terms will be equal to 0, and we will get this W-11. Similarly, we can, in this case, derivation of U2 with respect to H1 we will get this value. So our final outcome of derivation of E with respect to H1 will be E1 into, here E1 represents the error at node 1, E2 represents the error at node 2, and this is not exponential function, and W-11 is the W-11 is the weight of neurons from H1 to O1. This is already clear. So this is the final score for derivation of E with respect to H1. Now the next part is derivation of H1 with respect to W11. So derivation of H1 with respect to W11, for this we need to put the value of H1 from the actual calculations that we have here. So we will copy this part, with that we copied here, and we take the derivation with respect to W11, which is x1. So now the entire error is this. Now we will use this gradient to update the weight of the neuron. So the new weight of the neuron W11 can be given by old weight of neuron W11 minus new, which is learning rate, into this gradient that we calculated here, and by using this we can update the weight of neuron. Similarly, we can update the weight of all neurons, or in summary we can say that we can update the weight of entire all elements of this matrix. We will repeat the entire process. We will repeat the entire process of forward pass, error calculation and back propagation until we get the optimal weight of all neurons. And after that we will apply the next phase, which is the test phase. We will just pass the input value, and the test phase is very simple. As in the traditional artificial neural network, it is just a forward pass, and after the forward pass it will generate the prediction probability, and based on the prediction probability we can identify the missing word for the given context word. Now let us see some general architecture, general representation, which is collected from these references. So this is the input layer, this is hidden layer, this is output layer. Continuous bag of words based model with only one word in the context, in generalized representation that we generally use in all papers and textbooks. Now let us go through a more generalized representation of continuous bag of words based model. Input layer, hidden layer and output layers are represented. The nodes of hidden layers H1, H2, Hn are represented. These are the input layer nodes x1 to xb, and this is the weight matrix. This is another matrix, and this is the output layer nodes y1 to yv. Similarly, we can see the continuous bag of word based model with multiple context. So here we have used total k context. So our input layer contains total k context inputs. So this is the first input, and this is a mirror representation of this input context, and this is the hidden layer part, which is entirely same, and this is the output layer node, which is almost same like this output layer node. If you want to go through the entire architecture in more detail, then you can follow these references. Hope you have enjoyed this lecture.